可以开始了。Okay, first I would like to welcome you to join this session. I hope you had a good lunch and enough coffee so that I don't hear any strange noise here. I'm William from a local ISP, Chief Telecom, and we are a group company of Zhonghua Telecom, and we also operate the biggest internet exchange here in Taiwan. And first, I would like to introduce the first speaker, who is from the local Taiwan as well, the National Jinan University. He's a doctor named Yingjie Zhang, Zhang Yingjie 博士, okay? He's going to share with us the SDN-based security mechanisms on the new 100 gig backbone of Taiwan academic network, which is the biggest I think it's a public sector network in Taiwan. So let's give a big welcome to Dr. Yingjie Zhang. Yeah, please.
Good afternoon, ladies and gentlemen. Thank you all for being here. Today, I would like to talk to you about SDN-based security mechanism on the new 100 gig backbone of Taiwan academic network. Okay, part one, TANet's challenge for security mechanism. Taiwan Academic Network, TANet, is a national computer network for educational and research purposes that was established in July 1980 by various major universities and the Ministry of the Education, MOE. Its main objective is to facilitate teaching and research activity for school and research institutions of all levels nationwide in an effort to share resources and provide opportunities for cooperation. Certainly, the TANet environment is jointly managed by the Ministry of Education, the National Science Council, and academic SNICA in order to provide schools all of levels with an information infrastructure for application in the area of education. Learning and academic research. TANet network framework. Domestic includes domestic backbone network, international backbone network, inter-school network, and external network, wireless network in school campus, and security. More than 10 years ago, TANet network topology was three-tier topology. We have 4 core nodes at Taipei, Hsinchu, Taichung, and Tainan. 13 regional center and 22 country network center. Until 2016, TANet have all new network framework. We have we have a new router, new dark fiber backbone, new power system, new network measurement. This is the main point I want to make today. When throughput upgrade to 10 GB, 40 GB, 100 GB, a lot of existing devices have no 10 GB port, although they still work well. Interface speed only 1 GB, for example, firewall, IPS, or IDS. Problem is we need to buy new expensive device. 10 GB, 40 GB, 100 GB security device is usually more expensive than router and switch, while comparing the cost and bandwidth. Don't worry, however, we have a good idea. Please allow me to introduce my partner, Tony Wang. Let's now take a closer look at SDN-based security mechanism on the new 100 GB backbone of Taiwan Academic Network.
Hello, my name is Tony Wang, and I'm from the PackX Technology. So right now, I would explain the detail about how the SDN-based security supporting mechanism can save our questions. Okay. This is a concept diagram for today's network. In the left side, you can see it's the regional network center. Actually, it's a campus network, and the right side is a Telnet backbone. So we can see the core router is a 100 GB core router. So in the purpose we have to do is we want to put the IPS in this system. So the first challenge we will see is that if you see the Telnet core router site, it's 100 GB interface. So it means that if you would like to put the inline IPS in this site, it's not possible. So what we do is we make a loop, so that all the traffic between the Telnet and the regional network center should route the IPS. Sorry. So the traffic will like this. Go to the IPS and go to the Telnet core route, the backbone, and the reverse. Okay. So that we can make sure all the packets, all the Ethernet stream will go through the IPS. But obviously, we can see there is a single point failure threatened in this diagram. So this is not a good idea. So what we would like to see is this one. This is a new mechanism. In this mechanism, we added two components. One is a bypass switch, and one is a proprietary SDN device. So, okay. Again, we see the Ethernet packet flow. It's from the regional network center and go through the IPS and then go to the Telnet core. And then, again, reverse. So, what we will play, why we play the bypass switch here is because it's an optical switch. It means if any point failure, the traffic will still pass the bypass switch and go through. So, for example, if your IPS is crushed or maybe power off, the internet access it could be still sustained. So this bypass switch should provide a health check in case any element malfunction. It means the bypass switch is not only a dummy device. Actually, it will send the heartbeat packets. And they are both sides. So if the another side did not receive the heartbeat packets, it means something wrong. So we will use the heartbeat packets to check if the internet access is still work. Okay, so when some trouble happens, the Ethernet packet stream will never go to the IPS, and then directly bypass the IPS and go to the tiny 100G backbone. This is why we should put the bypass switch here, because we would like to avoid the internet connection broken in any situation. Okay, so, but the critical issue is when IPS cannot sustain for the network throughputs. I think we know that the security appliance processing power cannot catch up, can not easily catch up the internet throughput today. And it also means the budget issue. So, for example, we can consider maybe like a 4K stream, or a lot of the YouTube packets. Usually, it's a bandwidth killer, but actually it's low risk. So the idea we would like to propose is about the service bypass, or we call the application bypass. So the SDN device directs the YouTube packet not to pass through the IPS or IDS, but loop back directly. So in this case, we force the traffic bypass the IPS instead of IPS value itself. So, of course, not only for YouTube, we can consider other kind of the maybe multimedia stream or something like or some like advertising URL link. We can let those traffic does not get into the IPS to save your IPS power. So the proprietary SDN device may help to reduce IPS loading. So we could extend the period of the use of IPS. Yeah. So I think it is very important is because the first challenge we have right now is always the bandwidth. And the bandwidth is increasing. And usually it means your security appliance processing power should be increasing too. But the problem is, does the IPS really get the packets of its interest? Or, for example, beside the IPS, for example, we put the web filter in this diagram. For when we consider the web filter, usually we may consider only port 80 or port 443, which means the other packets, the web filter never cares about that. So if so we have to avoid those packets to get into the security device, because it just make it just kill your CPU loading. Okay, this is a technical idea about how to do the YouTube bypass. So the key idea we would like to say is we should distinguish YouTube packets from the input Ethernet streams. So that is, it is kind of a classification. You will have the two categories. One is YouTube packets, another one is the other packets. So how can we do this? First of all, we have to do the configuration. In this system, we have to insert the YouTube signature. And then when the system is on, the packets coming, if the signature can be matched in some packets, and then we will know the stream can be YouTube stream. And then we have to learn the server IP address of that packet. And then we put the IP address into our IP table. So next time another packet comes, and we will see if the packets can match the IP. If matched, it means it's YouTube. So then we just bypass that. So of course, the IP table should be refreshed frequently. Okay, so to make sure our IP table is consistent for the YouTube service today. Okay, another case we can do is about Lopez functions. So Lopez function could direct traffic to a few of IDS simultaneously according to like IP address, subnet, or 5-tuple hash. And then SDN device could accurately deliver different application traffic to different IDS or any kind of out-of-band analysis system. So this makes new security testing or forensics process easier. So SDN device can also be, so actually the SDN device we talk is a kind of the monitoring infrastructure. It is to support both inline security function and out-of-band security functions. So just like the diagram you can see, you can support the IPS, you can support the IDS or other kind of it doesn't matter, it's inline or out of band. So some guy, they may use the service chain. For example, they have IPS, and then they have a web filter, and then they have the DLP in the same inline. Okay, we can also support both conditions. We can support that according to the SDN mechanism. So then we would like to talk the SDN-based security supporting infrastructure. The second part is about the net flow generation. Okay, I think we know that the router can generate the net flow, but the problem is routers hardly support one-to-one non-sampling net flow generation. Yeah, usually it is okay because if your concern is about network management. But if your concern is about security, so then sampling net flow may not be a good idea. So one-to-one non-sampling net flow generation will be very important. But the router, they have their main job. Net flow generation is not their main job. So they cannot do that so good. So in our case, we can get the traffic from the router, no matter it's from the inline or out-band. And we analyze the traffic and generate a net flow. So right now, net flow, maybe we can use V5 or V9 and send it to the flow report server. And the flow report server actually, so you can use Arbor, you can use Lancope, any kind of the net flow analysis system. And this will help to reduce the router CPU usage and improve the security level. Because if you have a one-to-one non-sampling net flow, you can find more. For example, we usually talk about something like the DDoS or APT. It means we would like to know more details about the behavior, and we would like to detect any threaten, any attack as early as we could. So so one-to-one non-sampling net flow could help us to do that. Okay, so we can see a comparison. Oh, so left side you can see is today. So traditional net flow generation architecture. The one who was responsible for generating net flow is by router. So maybe it's 64 to 1. It means 64 packets, and you will check one, and then generate the net flow. But today, in Jinan Daxue, it's in the right side. It's the router's traffic is come to the SDN device, and the SDN device, they can do the filtering first. Yeah, you can consider if you would like to filter first or not. Just like we say, if we think some traffic like maybe YouTube or maybe Netflix, you think, it's a trouble for the network management, but it may have little security concern. So we can filter those traffic. And then after that, you generate net flow from the traffic depth. So in this case, we can generate net flow no matter version 5 or version 9. And the sampling rate is 1:1. Active timeout and the passive timeout could be, maybe you can just use 60 seconds or maybe less. It depends your computing power for the analysis, for the net flow analysis. Okay. So in this case, we can see if IPS is out of, if this we could, if IPS is out of service, so that bypass switch state is changed to the tape mode. It means, in this case, the traffic can never go to the IPS, but the bypass switch become a tape. It will mirror the traffic to the SDN device, so that even IPS does not work, the SDN device still can generate net flow. So it could be quite important, because we know we would like to see the traffic cannot be inspected by the IPS. But in some cases, you have no choice. But at least you can have the net flow. So now is our conclusion for the mechanism we propose to you today. The SDN-based security supporting mechanism, they have high availability because they can work with the bypass switch, and then it can do a load sharing. It can distribute the load to several IDS, IPS, no matter it's out of band or no matter it's inline, simultaneously, and it's cost down. I think it's very important, because it can check maybe some traffic. It should be okay. Should be in your whitelist, so you don't need your security appliance to waste their CPU power on them. And the final is the flexibility, because we know the security device will be more and more, because the quite a lot the cyber threaten attack today. So maybe you will consider the service chain inline security appliance, and maybe a more out-of-band security device. So SDN-based security supporting mechanism can support those situations and make our life easier. Thank you.
Okay, thank you. And do you have any questions? If you do, please, there are microphone stands at the back, and state your name and which company or which organization you're from. Any questions to the speakers here? I guess not. Okay, so let's thank Mr. Zhang Yingjie and Tony again for the sharing with us.
Thank you.
Okay, our next speaker is Jonathan Brewer. He's from Telco 2 Limited. He's a consulting engineer, and he began his internet career in Kansas, And he moved to New Zealand in 2003. And wow, he done a lot of good jobs about the wireless and satellite kind of things, which I don't really understand. So I look forward to hearing from him, and I hope you enjoy the speech from him as well. Yeah, let's give a big applause to Jonathan.
Yeah, thank you. Thank you very much for that. They're just arranging my display here so that I know what to say to you. So as you can tell from my accent, I'm from New Zealand. I have lived in New Zealand for 14 years. It's a lovely place, but I'm very happy to be in Taichung. So look, we're going to talk today about satellite. And there are a few points we're going to cover, but really what I want you to take away from this talk is some language. I want you all to learn 3 terms about satellite orbits and 3 terms about satellite spectrum. We're going to talk about these terms throughout the presentation. So first off, why do we need satellite broadband? What about distance and latency? Spectrum, satellite spectrum, rain fade, speed, architecture, resilience. These are all of the things we're going to talk about, but first we're going to talk about why do we care? This is easy. Why do we care? So on the x-axis here, we've got population density from 0.1 people per square kilometer all the way up to 100,000 people per square kilometer. And then we have on the y-axis a relative cost and complexity figure. And in colors, do we see these colors? Yeah, in colors here we've got fiber optic in red, cable modems, ADSL, fixed wireless, and satellite. This chart is a little bit old. Canadian Communications Resources Canada, CRC, published this maybe 15 years ago. I've adapted it and put some New Zealand stats up on there. But look, it basically says that the further away from city centers and the lower your population density, the more costly and complex it is to use anything but satellite. Satellite's a nice even curve there. It kind of hardly matters how fine or sparse the population is. So that's the why. Why do we need satellite? Why don't we want satellite? This is easy. Now, places like Australia or the US, it's easier to make this metaphor here, but people buy horsepower when they're shopping for cars, but they drive torque. They feel the torque of the car when they accelerate. Now, when people buy internet connections, they buy megabits. They say, oh, it's a 25 megabit per second connection. But really what they notice when they're surfing the internet is the latency. Latency matters a lot to broadband. How much? All humans notice latency, and this is a chart of 41 million samples of people reacting to things on the internet. Once you get to, say, 320 milliseconds, the majority of people in the world are going to notice that it is slow. This is science, not opinion. So don't let satellite salespeople tell you that nobody notices the latency. In fact, once a web page takes longer to load than 320 milliseconds, everybody's going to know it's slow. Once a voice conversation has a pause of 320 milliseconds, everyone is going to know it's slow. Now, satellite, people don't like satellite because latency is related to distance, and most of the satellite that happens in this world today is in a geosynchronous or geostationary orbit. That's the one way over on the left here, 36,000 kilometers, and I took that graph from that chart from the last slide, and I plotted it here. And I showed here's about 320 milliseconds. Here we are all the way at about 480 milliseconds. When you download information over a geostationary satellite link, you send your request up to the satellite, it sends it back down to an Earth station, it goes out to the internet, it gets the traffic, back to the satellite Earth station, up to the sky, back down again, and by the time that's happened, you've spent at least 480 milliseconds just in the air, not going out to the internet and getting your data. So everybody notices it's slow. Now they won't so much notice it's slow in some different orbits. So these other orbits that we'll talk about a bit later are the low Earth orbit and the medium Earth orbit. Here's our geostationary or geosynchronous up there. So satellite is slow. Game over, we give up, right? Let's step back and learn something about satellite, and then hopefully get you all excited about the new things that are coming in satellite. So, I do a few things with radio in my life, a lot of things with radio and wireless, and it happens that satellite is entirely radio and wireless. It just happens that your cell phone tower or your base station is up in the sky and not up on a hill. The great things about radio waves is that radio waves travel in air at nearly the speed of light, and that is a lot faster than they travel through fiber optic cables. You put a light signal down a fiber optic cable, and it goes 40% slower, 33% slower. So this is because the light's actually bouncing around in there in that glass, and it's slowing down. It's not in free space. Now, the bad thing about radio waves is as they go through air, other things share the air. Rain, snow, birds. Now, when you're out in space, none of this happens. But when you're here, between here and, say, 10 or 15 kilometers up in the air, you've got all of these other things to contend with, probably including Elon Musk, who's flying around there with his rocket ships and his spacesuits. Now, the neutral things about radio waves is that different frequencies have different properties. There's no such thing as bad radio spectrum. All radio spectrum is good radio spectrum. It just has different properties. Bigger radio waves, which is lower frequencies, behave quite differently from smaller radio waves, which are high frequencies. Here we got a chart that shows you where the satellite bands are, and now we're up to our next three terms. Our first three terms were the satellite orbits: low Earth, medium Earth, geostationary. Our next three terms are C-band, Ku-band, and Ka-band. Oops, back. There's my laser. So here's C-band here. Here's 0 gigahertz and 10 gigahertz. Here we've got our cell phone frequencies. 2G, 3G, 4G are here. Our Wi-Fi, here's our 2.4 gigahertz Wi-Fi in this little spot. Our 5 gigahertz Wi-Fi in this spot here. C-band goes from about 4 to 8 gigahertz. Ku-band goes from about 12 to 18 gigahertz. And Ka-band goes from 26 all the way up to 40 gigahertz. You don't see any cell phones or Wi-Fi going on up here. Why wouldn't you put cell phones up here? Well, we'll talk about that in a bit. Anyway, notice that Ka-band has a lot more spectrum than C-band or Ku-band, and that's important. Here's a primer on the spectrum. You download this and refer to it later. But in terms of spectrum availability, we have a lot more spectrum available in the Ka-band. Reuse, which we'll talk about in the next slide, we have a lot more reuse in the Ka-band. Antenna size, we'll cover in another slide. Our antennas are much bigger in C-band than they are in Ka-band. And then rain fade. We hardly have any rain fade at the C-band, and we have heaps and heaps of rain fade at the Ka-band. Now, reusability. Reusability is the ability to take a piece of radio spectrum and use it twice from the same broadcaster, from the same tower, the same satellite. So in this case, I've got a picture of a C-band beam coming from a satellite, and it's covering most of Western Australia there. That's one frequency. We can't reuse that frequency again within that area. But it happens that Ku-band, the waves are much smaller than C-band. You can actually reuse that quite a lot, about 4 times as much as C-band spectrum from a geostationary orbit. And Ka-band again, you can use the same spectrum for Ka-band about 20 times in an area the size of a C-band transmitter. So very high reusability, and that means you get more bits out of your spectrum. Now, antenna size. Higher bands have smaller antennas. Ka-band has an antenna that's 1/16 of the area of a C-band antenna for the same amount of gain. Now, gain is this concept of amplifying or concentrating radio waves, because antennas don't actually amplify anything. Antennas concentrate radio waves. If you think of a candle, see this clicker right here is a candle, and I stick a reflector behind it. Now, if I use a really small reflector, I might get a huge, wide beam of light that's very dispersed. If I stick a big reflector behind it, I might get a pinpoint of light all the way on the other end of the room. Well, look, to get an equal amount of amplification at these 3 bands, your C-band antenna is 16 times the size of your Ka band. This can be quite big. Now conversely, with the same sized antenna, we get a lot more gain in the higher bands. So here we have 3 antennas, and imagine I'm holding a 1-watt light bulb. Well, in C-band, I'm getting 1,000 watts of amplification or concentration out of this 1 watt. In the Ku band, I'm getting 4,000 watts. And in the Ka band, I'm getting 16,000 watts. Huge amount of concentrated energy in the Ka band because the waves are so small. These are very, very striking figures. And now it seems like Ka band is the win. So the dishes are smaller, you get more gain out of it, you have more spectrum reusability, fantastic band, and the only problem is that higher bands mean more rain fade. A lot more rain fade. Just how much more rain fade? This is a very, very dense chart, so download this if you're really interested. But we've got rainfall here in the right-hand side y-axis in millimeters per hour. Now that 100 figure up there, that's like typhoon. The rainstorms in Texas last week were putting about 96 millimeters per hour down. In Florida, they're probably coming up on 60, 70 millimeters per hour. Down here at the bottom, we've got 0.25, a gentle rain. Look, what this tells us, here's Ka band in orange, Ku band in yellow, and C band in green. What this tells us is that in almost any sort of a rainstorm, this is raining here, 2.5 millimeter per hour. So a gentle rain, we have absolutely no impact on the C band. We have a little bit of impact on the Ku band, and we have a huge amount of impact on the Ka band. Huge, huge, huge amount of impact on the Ka band. In a proper rainstorm, even in the monsoon stuff, C band's not affected, Ku band's not really affected. Ka band just has terrible, terrible rain fade properties. So if you're in a tropical region, you should expect that every time it rains, your Ka band satellite service is going to go away. It may not go away for the whole rainstorm. It may go away for a minute or two. But over the course of a year, most Ka band services for tropical regions are engineered to work 99.7% of the time. Now that means many, many hours a year of downtime due to rain, and it's not going to be big, long blocks. It's going to be every time it rains, you lose your service for a minute or two or 5 minutes, which, you know, some people can accept that, and some people absolutely can't. Meanwhile, your C-band service is just going to keep going. So why doesn't everybody just stick with C-band? Now here is a comparator, a straw man. I say with the same amount of resources, you can probably get a 512 megabit per second Ka band service that'll work 99.7% of the time. Or you could get a 64 meg Ku band service that works 99.9% of the time. Or you could get a 16 meg C band service that works 99.995% of the time, or maybe even better. What are you going to do? This is a choice that you have to make. So we're going to talk about architecture next. How does satellite architecture work? In the most basic of satellite systems, you go up, you go down. Little square is the customer. The big yellow square is the Earth station, and the internet connects to that Earth station, usually by fiber optic cables. So you can have your up and down. You can have 2 ups and 2 downs, redundant VSAT connections. And if you build your network right, you connect those 2 Earth stations with a fiber cable, you balance your traffic across them. Now I have this thing I'm calling multimodal here, which means maybe you'll use a geo-band service and a MEO-band service. You'll combine the 2 services, or a LowEarth Orbit service. Now I have this picture called multimodal with a fiber link. And you might say, well, why the heck would we use satellite and fiber at the same time? Well, you might use satellite to back up your fiber connection in case it gets cut. Or in the case of American Samoa and their telco Azteca, you might have run out of capacity on your fiber circuit and you're using satellite to supplement that. The way Astica has their network set up, they have a satellite link to Hawaii and a submarine fiber cable to Hawaii, and they connect the two POPs together with fiber, and they balance the traffic across the two circuits. Now these are pretty standard architectures for broadband satellite. We have some advanced topologies that are coming into play now, and one of them is where the satellites actually pass the traffic through space down to Earth stations that are too far away. So this is happening with new networks that are launching, like the Iridium Next network. 20 satellites for Iridium Next have been launched this year, and we'll talk about specific cases for satellite crosslink in a few more slides. The next architecture here is cloud avoidance. In tropical areas like the Pacific Islands, Rarotonga is a very good example of this. You find that it doesn't rain in the same intensity all over an island at the same time. Rainstorms usually come across in big waves, and you get big waves of highly intense rain in one place and not the other at the same time. So in Rarotonga, what they've done is built 2 satellite Earth stations. They've connected them together with a fiber cable. And what do? But they take the best signal from the satellite and decide, well, that's the dish we're going to be using right now. They route all of their traffic over the best performing link. They've done this in Solomon Islands. They've done this in some other examples that I don't have public mention of, but it is a very valid topology, and people have started using it in the last year or two. Now we're going to talk about the orbits. Half done now. Back to the orbits: LEO, MEO, and GEO. LEO, low Earth orbit; MEO, medium Earth orbit; and GEO, geostationary or geosynchronous orbit. Geostationary orbit is when the satellite is straight up overhead and it rotates at the exact same speed as the surface of the Earth. So it must be going quite a bit faster than the surface of the Earth as it spins around in space, but it's staying overhead all of the time. It never moves. When you have a satellite like this, which needs to be around 36,000 kilometers away from the Earth, you're going to get coverage of most of the Earth, plus or minus 82 degrees. That means that you're not going to see the poles. The North Pole, the South Pole. You don't get geostationary coverage from geostationary satellites at the North Pole or the South Pole, but plus or minus 82 degrees covers almost all of the people living on Earth. Geostationary is mass market satellite. It's what people use for broadcast television, satellite radio, data services, telecommunication services. You get more than 400 milliseconds of latency, typically 480. So that's geostationary. I'll give you an example of some services in geostationary. This is a very New Zealand specific or Australia, New Zealand specific example. Optus D2. Optus is a satellite that went up in 2007, and very typical for satellites of this era, so 10-year-old satellites. The most internet bandwidth you could get out of a channel is around 540 megabits per second. And now at its peak, this company, FarmSite in New Zealand, was sharing that with 16,000 users. So they were taking that 540 megabits per second and sharing it by 16,000 users. Not a great experience for anybody. And in fact, back then, I think they got a little bit less than 540 megs out of it. These days, they have fewer users, and they provide peak speeds of around 16 megabit per second down, 2 megabits per second up in that bit of spectrum. This satellite is expected to last until 2022, and then it's going to run out of fuel, and it's going to fall back to Earth in a fiery cloud. Hopefully it doesn't land on Bertrand. Hi, Bertrand. Okay. Now, the next generation of satellites we've got, also a very Australia, New Zealand specific example, is Australia's Sky Muster. And let me step back here and just show you this Optus satellite. This satellite here weighs 1.1 tons, metric tons, so 1,100 kilos. This Sky Muster satellite, you see those guys over there? You see how tall they are, and you see how big this satellite is? This thing weighs 6 tons. It's like the size of a bus. It's absolutely gigantic, but it has a lot of capacity. It's a Ka band satellite, so it uses these very high frequency, very small waves that are very prone to rain fade. But out of those waves, it gets 67.5 gigabits per second, and they've got 2 satellites up there. So they're putting 135 gigabits per second of capacity down just on Australia with these 2 satellites. And they're offering 25 meg down, 5 meg up plans, and I think people can download, 400 or 500 gigs a month on this without going outside of the bounds of their plans. If you are living in the parts of Australia, I'm going to go back. If you're living in the parts of Australia that are, say, over here, in here, anywhere except the very edges, Sky Muster is going to be just phenomenal. It's going to be fantastic because it's really, really dry there. But once you get up here, this is basically like being in Indonesia. It rains, and boy, does it ever rain. And the service there for Sky Muster is just really bad because every time it rains, it stops working. So, kind of what you get. Back to our click, 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 click. There we go. They have so much capacity, they're bringing it down to 10 different Earth stations in Australia. Each of those 10 Earth stations are located near the major population sensors and connected with fiber. The dishes they have at these Earth stations are gigantic. They're probably, as big as this part of the room. Just huge, huge dishes. So that's our geostationary orbit. I'm going to talk about medium Earth orbit now. And we've had broadband satellites in medium Earth orbit since 2014. There have been other types of narrowband communication satellites in medium Earth orbit for a very long time now. But broadband use only started very recently. Medium Earth orbit, we're closer to the Earth again. So we only get plus or minus 45 degrees coverage. Here we're about 8,000 kilometers away from Earth, up to about 12,000 kilometers away from Earth. Now to cover the Earth at 45 degrees plus or minus, we need to have at least 8 satellites. And the satellites are not just sitting up there overhead, they're actually whizzing around the Earth, and you might have a satellite go by you every 90 minutes or even more frequently. So if you're down on the ground, you actually need to have a dish that tracks the satellite as it goes through the air. Now here's an example of a MEO network that's in operation now. O3b, who really revolutionized telco networks in the Pacific, and honestly are the company that got me interested in modern satellite systems. So what happens with O3b? But every end user has 2 dishes. One dish sits pointed at the horizon, waiting for a satellite to come up. The next dish is locked onto a satellite, slowly moving across the sky with the satellite. As soon as another satellite comes over the horizon, the second dish locks on, start running the traffic on both, and they use BGP to switch over. BGP. This is a network conference. I love that they use BGP to switch over traffic feeds between the 2 satellites. Just fantastic. So, 144 gigabits per second of traffic online. O3b are the biggest supplier of broadband into the Pacific right now. They've beat all the fiber cables. They have been so successful that they've ordered another 96 gigs of traffic of satellites will be launched in the next couple of years. The way it works is each one of these dishes, these are quite small dishes up here, each one of these dishes can provide 2 600 megabit per second beams, so that's a total of 1.2 gigabit per second. And by the time it hits the Earth, the size of the footprint on the Earth is 700 kilometers. You get rain fade even if you have a 4-meter dish, which is why countries like Rarotonga, Cook Islands, I should say, have started putting 2 dishes down and linking with fiber. So as you can see, this is not a big satellite. It's 450 kilos. So all of this, the O3b satellites put together, still weigh significantly less than that one Sky Muster satellite. These are cute little things. So next network here is has not launched yet, but is one of the most interesting networks out there. Laserlight plans to be the world's first all-optical satellite network. It's going to be in the medium Earth orbit, and it will be the fastest intercontinental link. The fastest way to get from Los Angeles to Sydney is going to be through the air. on lasers, space lasers even. This is a company that probably has good prospects in financial markets. For military users, it's very hard to intercept laser traffic. And they're going to take advantage of the same technology that O3b is using in Cook Islands by hopping their laser beams around metro areas to avoid clouds. But instead of having 2 dishes connected by a single fiber optic, they're going to have 10 or 12 receivers in each metro area. And they're going to tend to build these metro areas in quite dry places so that they can keep their signal up all the time. Each one of these satellite beams is going to be 100 gigabits per second. And each one of the connections between satellites, so here we go like this, is going to be 400 gigabits per second. Same technology, but when you go through space, you don't have any molecules of air to contend with. You can actually run your links quite a bit faster. So Laserlight's going to have 7,200 gigabit laser heads from their satellites pointed at the Earth, 7.2 terabits per second of bandwidth. Quite big. Now we get into low Earth orbit. This is our last set. Iridium, Globalstar, and Orbcomm are all low Earth orbit satellite phone networks. These are all in polar north-south orbits. So instead of going around the equator like the medium Earth orbit satellites go, these guys go up and down. And you need tens of satellites to make this work. You do see the poles. So low Earth orbit networks are pretty much the only ones that we've talked about today that have the ability to cover the poles. And this is the next space race because everybody is interested in low Earth orbit. First one I'm going to talk about here is OneWeb, who are focused on the consumer market. They were invested in by Airbus and Boeing and Coca-Cola, Qualcomm, Virgin, and more recently SoftBank, who last year put $1.2 billion into it. They plan to launch 700 or more tiny, tiny satellites, like satellites so small and so light that I could hold them in my hands and show them to you. Little tiny micro base stations in the sky, each of which is going to have 6 gigabits per second of radio capacity facing down to the Earth. So they're building a 4.2 terabit per second network. Intelsat has already invested in OneWeb, and they plan to offer blended service, C-band, really reliable, low bandwidth, along with this KU band, which is less reliable but much higher bandwidth service. Next one we've got here is LeoSat, which is enterprise focus. They're looking at selling circuits to oil rigs, trucking companies, remote minerals and mining facilities, backups for banks, urban areas that are worried about fiber cuts. They share the same satellite platform as O3b and Iridium Next. They're going to launch 78 satellites in 6 orbital planes. They're going to use lasers to connect between satellites, so the cross connect, and it's going to be a 1.2 terabit per second network. Now the last one is the most ambitious, most audacious network ever imagined. SpaceX and Google are looking to launch 4,425 low Earth orbit satellites starting in 2019. They're going to use space lasers, optical cross-connect between the satellites. They're going to offer a 1 gigabit per second broadband service to any point on Earth. And they're building an 88.5 terabit per second network. This is an absolutely astonishingly big network. And guess what? SpaceX happens to be a rocket ship company. All they do is they put satellites into orbit. You take a step back here and we look at LeoSat. They're a joint venture with Thales and Thales Alenia Space. It's a rocket ship company. They launch satellites into space. We go back here, we look at OneWeb. One of the major funders of OneWeb is Virgin, as in Virgin Galactic. They're also a rocket ship company. They launch satellites into space. Virgin has just repurposed one of their Boeing 747s so they can do aerial launch of these satellites. They're going to strap a little rocket to the bottom of their 747, fly it up into the air, and drop the rocket. Launch 20 satellites at a time that way. So this is really a space race. We've got 3 This is 3 of 7 different companies planning low Earth orbit satellite networks right now. The amount of satellites that we're going to see in the air, well, in total, I think we're going to have more than 10,000 satellites in the air in 5 years, and today we have around 1,000 satellites in the air. So we're going to go up by an order of magnitude in number of satellites. We're going to go up by, I think, 3 orders of magnitude in the amount of internet bandwidth or IP bandwidth facing the Earth because of these new networks. So that is it. I do believe the future is up in the sky. And that's my 30 minutes and 6 seconds. So if you have any questions, please ask them fast. Oh no, it's a Jeff Houston.
Do something with the microphone, thank you. One comment and one question. You didn't mention the Van Allen belts, and part of the reason why not all of that orbital space is occupiable is that between them, sort of where the MEOs are and the GEOs, is a bunch of highly irradiated ions that will destroy anything. So not all of these orbits are accessible. But there was one question and one comment you made which kind of intrigued me about station keeping fuel and how long these things stay up there. So obviously something that weighs 64 tonnes is going to use an awful lot of hydrazine to keep on positioning itself against the moon up in geostationary. But when you've got these tiny little bastards just above the atmosphere, and even if you had a litre of hydrazine, how long are they going to last?
5 to 7 years for the very smallest satellites. However, if you look back to the Iridium network, which was launched in 1997, 1998, those satellites were expected to last 10 years in orbit, and they've ended up lasting 20.
Well, they're still flying, so I kind of wonder.
They are still flying, so the design life of these new LEO networks is typically 5 to 7 years. However, who knows how long they'll last.
Cool, thank you.
Okay, any questions? Please.
Well, following that, if the satellites stay in the sky for 6 or 7 years, and then at that time it's 5,000 satellites drop back to the Earth, what will happen?
I believe they're nice and small, and they're going to burn up quite quickly, and we're going to have some beautiful meteor showers at night. Shooting stars. Good luck.
Alain Durand from ICANN Office of the CTO. One of the things about spectrum is the higher going frequency doesn't play well with raindrop, but it doesn't also play well with things like trees and leaves and roofs. And can we expect some kind of an hybrid system with cell phones and a radio tower that will maybe shoot up to the sky? Or should we expect that all the handheld device will shoot directly up to the sky?
Typically with the higher frequencies, you're not going to have direct to satellite. You're going to have a terminal. The OneWeb offering so far is a panel, probably a meter, that will lie flat on your roof with beamforming antennas. And inside you'll have a Wi-Fi and or LTE base station for your home devices to connect to. So it will be like having a hotspot. Now they've also designed an antenna for car roofs, and they've built it into a Toyota car roof already. The company there is Kymeta, and they've built a Ka band antenna for cars that's designed to work with the OneWeb system.
Thank you.
You're welcome. And none of these systems will work through trees. They all have to have a clear view of the sky. However, the low Earth orbit networks have so many satellites that view of the sky can be as small as a 20-degree arc directly above you. You don't have to have a very wide view of the sky to make a low Earth orbit satellite network work, unlike for a medium Earth orbit where you do need to be able to see most of the sky. I think we're done.
Yes. Yes.
for your
Any more questions? Okay, let's thanks Mr. Jonathan again for his great speech. I learned a lot from him, really. So our next speech is simulating the network dynamics of shared satellite channels. And our speaker is Mr. Ulrich Bader. I hope I pronounced it right, but I guess not. He's from University of Auckland, and he's a senior lecturer. So let's give him a big welcome. Thank you.
Kia ora tātou. Thanks for coming, and yes, thanks also particularly to John here for giving such an incredibly good foundation on satellite systems and also on what to expect. So I'll be able to whisk really through some of the slides here because it'll be so straightforward. Okay, so basically, as John's explained, a lot of Pacific places in particular have the problem that they're small, reasonably poor, and far away, and so laying a fiber optic cable in a lot of cases is not economical, not an option really. And so what do we typically deal with? Internet connections that go either these days via GEO or MEO satellite. The deployed capacities inbound into the islands could be anywhere between about 2 to 100 megabits per second, and very common characteristics is, and this is something that John did not talk about, but that I'll concentrate on here, is that we'll be sharing this thing with multiple TCP flows. And when I say multiple TCP flows, I'm not talking the 2 or 3 or 4 that you typically see in scientific papers. I'm talking literally dozens to hundreds of parallel flows, and not all of them are long enough to be subject to TCP flow control. So problem that we have here is that we've got very little economy of scale. Now, just to give you an idea, when you talk about the Pacific, and I really like it that APNIC puts the P of Pacific right into the middle of its acronym, because typically when you go and you Google world map, then this is what you get, and half of the Pacific doesn't show half of the time. And so if you're from the Pacific, you can be forgiven for feeling a bit marginalized. Okay, now let's look at this from the view of a GeoSat provider. Now, if you're looking at the Americas and you're sitting above the equator on a longitude sort of matching up somewhere nicely with the Americas, this is the customers that you can see. Plenty of people, you know, remote in the Amazon basin, northern Canada, etc., and you know, lots of places to provide service to, lots of people to pay for your satellite and for your hydroscene and everything, right? So above Europe and Africa, when I was talking to people at the European Space Agency the other year, was very, very clear they had this sort of application in mind when they were talking satellites. Looking at a satellite sort of, you know, sitting, you know, more or less, you know, on the same latitude, longitude as we are here. And again, we're seeing quite a few customers. We're covering lots of, you know, rural areas, sort of, you know, even Siberia, you know, China, Mongolia, Australia, etc. So, you know, plenty of customers again to see. Lots of shipping as well. And this is above the Pacific. This is what you see. Now, to make matters worse, a lot of what you see already has cable, right? And really doesn't need satellite service in a hurry. So what still needs satellite service are things that by and large you don't see, and that tends to have sort of populations, as I said, in the few hundreds to a few thousands typically. So what happens if we feed TCP over satellite, and TCP is still the dominant transport protocol, believe it or not? We get an effect under certain circumstances called TCP queue oscillation, and it's characterized in terms of symptoms by link underutilization, so you're not able to use all that capacity that you're paying for, and it also is characterized by packet loss during the queue overflow phase. And this is really a very, very nice you know, thing to happen, in the sense that it basically slows any long downloads down enormously. Your TCP flows that go across those links are not necessarily long enough for that to happen, though. So when you're an ISP in the islands, then very often what you tend to do is you tend to check your connectivity, so you ping. And that usually works because, you know, it doesn't take a lot of packet loss in order to slow TCP down, but if your TCP flow is short enough, and a lot of flows, as we'll see in a moment, are, that basically, you know, doesn't slow you. That doesn't slow you down because you're still in the slow start phase. Okay, so Typically in TCP-Q oscillation, our packet losses are burst erasures. They happen when the queue overflows. And it basically happens as Q drops in the input to the satellite link. So it doesn't happen on the satellite link. You don't even get your packets to the point where rain fate could affect them. They don't even get into the air, so to speak. And basically, they're not usually caused by satellite-related effects such as the fading or noise or distortion. Basically, how can we tell? Turns out they stick to business hours, and fairly religiously so, even to the point that if you're looking on weekends where people don't have access to places where they can sort of sidestep the volume charging that they're getting at home, we don't see the effect occurring because the demand goes down. So this is a slightly older diagram from a Pacific ISP that I shan't mention here because it's not really relevant. And basically, they had a 160 Mbps MEO connection at the time, and I guess some people will probably then be able to guess who that was. What we can see is that we get a fairly flat profile during the day and then the typical drop during the night. But we also see that we have real trouble getting above 100 megabits per second. And yet the deployed capacity was 160, and no, it did not rain during that time. So basically, a quote from that telco, we have over half of our bandwidth sitting there doing nothing at the moment. And that was after they upgraded. So the one thing that we found, though, was that people did complain a wee bit about the service they were getting. And when I was trying to download large files there, I noticed that basically downloads were dying. So this is one of those neat little satellite stations, by the way. This is the formerly Telecom Cook Islands, now Blue Sky Cook Islands station on Aitutaki in the Cook Islands. And here you see the two O3b medium Earth orbit antennas. This is the old geostationary antenna from the link that previously carried things. And you can sort of see this is the antenna that's waiting for the next satellite to rise. That's the one that's tracking the current one here. And so we really get three scenarios. We get the low demand scenario where we get no Q oscillation, where the link is underutilized because there's not enough demand, and we get no packet losses there. Then we get the medium demand scenario where we get Q oscillation, we see the link underutilized, we see the burst packet losses. And then we get another scenario which I'd call the high demand scenario, which is characterized by standing queues, queue buffer bloat. Link utilization is almost 100%, and we get virtually no losses. The reason why we're getting virtually no losses is because in that scenario, our link is being used almost exclusively by very, very short TCP flows that are basically living with their first window of 10 or so packets, and that do mostly finish before the first egg comes back and they can change their congestion window. So question is, can we address that point number 2, which is one that we found a few times in the Pacific? So let's just recap a few facts about what network traffic really looks like. Firstly, most TCP flows are small, so and that includes things that we sort of do for casual, web surfing and this sort of stuff. Typically, your elements like thumbnails and bits and pieces like that, they're only a few kilobytes long. So they fit into a few packets. They fit in into your initial congestion window before it gets readjusted, right? So, and when we look at it, very, very few flows are in the 8 megabyte or larger capacity range, size range. And however, they contribute the lion's share of the data. So anything that's larger than that contributes basically over half of the data. But as it turns out, that doesn't sort of do what you'd usually expect from TCP, that if it has capacity available, that it basically goes and expands into that capacity, because in this case, what we would actually expect is that spare capacity to be taken up. It turns out, no, we're being throttled here. And what's actually throttling us is the TCP Q oscillation. So, again, I've sort of mentioned flow size a few times. So why does that matter? Matters mostly because if you have a conventional router, where you conventionally think about your bottleneck and the internet, then you get a wide mix of latencies. Now, the satellite latency is the one big chunk of latency, to and from an island like this that's shared by everybody who's using it, right? So small flows, as I already said, they're over before the TCP congestion control kicks in. So your last byte leaves the sender before the first egg comes back. At this point, there's no point in doing congestion control. And large flows, as I said, we're normally expecting to accelerate. But unfortunately, what happens is when they get knocked down on the head during TCP queue oscillation, they basically just slow down and they go down to an absolute crawl. And if we increase the demand, then basically what happens is we crowd out the large flows because they're the ones that respond and back off, and the small flows basically just take over. So the idea that we had is, well, let's have a look at random linear network coding and see whether we can do this. Now, basically this falls, at least the part of it that we're using falls basically under forward error correction. And if you've worked with satellite systems before, you know forward error correction is the thing you turn on your satellite link. Now the difference is the forward error correction that you're turning on your satellite link when your typical satellite engineer is the thing that protects your link against fading, rain fade, and bits and pieces like this. However, in order for that forward error correction to kick in the first place, in other words, for your forward packets getting, to get encoded, what actually happens is at that point they must have already been accepted into the queue at the satellite link. What we're talking about here, though, is packets that aren't even making it into that queue because the queue's already full, right? So what can we do? Well, basically, we can put an encoder somewhere in front of that queue, not necessarily immediately in front of the queue, but somewhere in front of that queue. And we can then apply forward error correction not within or for an individual packet, but across packets. And that allows us to deal with the loss of individual packets and still reconstitute them at the other side of our bottleneck. And that's essentially what we're doing here. So basically, the idea is you're having machines on the internet that sends traffic towards the island. It gets encoded here, gets then tunneled across in encoded form to a decoder over here, where the code gets decoded and the original packets get released to the end user machines. We do need a slight change to the normal topography here, in that the SAT gate needs to be sitting into a different sitting in a different network than the machines over here. Because what we need to ensure is that whatever traffic the web server here sends, or whatever it is, needs to go to the encoder decoder rather than to the SAT gate here. So basically, this needs to be the gateway to the network over here. So now, how well does this work? We already know that we can improve goodput for individual large flows that way. So this is an example from, again, that telco that basically said that they only had half their capacity available in practice. So looking at this, this is standard TCP over a day, and we basically did repeated downloads of, I think, 20 megabytes each, and this is the goodput that we're getting. If you're looking at the blue curve, during the day, we have a high packet loss, that's the black dots. The blue curve's quite suppressed, and the red curve is the coded form. So if we make sure we coded them, basically we ended up with, on average, goodput that was in the order of a factor of around about 4 larger. During the night, you can see it's much of a muchness. Why? Because we've got very low packet loss there. Very much, much of a muchness at that point. So the next morning, life kicks off again, and the cycle repeats. And you can see this going on day after day after day. So, question is, if we can do this for individual flows, can we do this for the whole of an island? So that's what we embarked on recently. And there are a few problems, right? For starters, if we move our encoder decoder to sit entirely in front of the SAT gate, we need access to the world-side satellite station, not just to the satellite station on the island, as we had beforehand. The other problem that we're having is, remember what I told you about needing slide topology changes? Well, we still need slide topology changes here, same problem as before. And now imagine going to a Pacific island and saying, hey, lovely islanders, you're great people, can I just unplug your internet connection for a day or two? Now, I know a lot of you are operations people. How long does it take between you plugging somebody's internet connection and them ringing you up, howling in protest? Not very long, right? So imagine doing this on a Pacific island. No way, they throw coconuts at you. I mean, basically, it's not on, right? So, so it's basically very, very difficult to test this in production networks. So we thought, okay, we'll go and simulate this. So the goal initially was replicate the problem scenarios, experiment with all of island coding using different parameters, and compare with performance-enhancing proxies like PEPs, which are a bit ugly. Now, the advantage of coding in some respects is that you can code transparently. So anything that goes in and anything that goes out looks as if there's just been a piece of cable in between, so you don't get sort of net-like or PEP-like, you know, renumbering, etc. So it sort of conserves the end-to-end principle rather nicely. Except that some of the stuff that you see in between doesn't look like the stuff that's going in and that's coming out at the end. But with PEPs, it's a different story. They're generally connection breaking. Right. So we want to be able to do this standalone and in combination. So what's the challenge with all of island coding? Now, imagine that this is the pipeline to the island that you're looking into, and this is the overall set capacity. Now, if you uncode it, that's the link utilization you can get. So if you're now coding a single flow, say you're initially having it uncoded, so it's your normal TCP, then that's the capacity that it takes up. If you start coding it, you're able to get more good put from the actual flow, but you also go along with some coding overhead. And the coding overhead and the extra good put now have plenty of that green belt to expand into. If you're coding everything on the island, then you have a potential challenge. And in fact, it's not just a potential challenge, it's a very real one. Basically, you need to deploy overhead, that's your brown ring, right? And then your yellow ring is the gain that you can get, and your green ring is whatever spare capacity might be left. So the idea is that if we're wanting to code, we're wanting to do it in such a way that that yellow ring is basically as wide as possible, the brown ring is as narrow as possible, so we can basically take most of that original spare capacity and put it into good put. And it turns out that this is actually something that we're struggling with. Well, why? For starters, we need to get the amount of overhead right. If we have too little overhead, we've got insufficient protection against packet loss, and the problem is that we need to protect against burst losses, which requires normally a significant amount of overhead. But these burst losses only occur very, very rarely. So a lot of the time we're actually transmitting overhead that's arriving on the island without ever having been needed. If we have too much overhead, then obviously we're getting the other problem. Our brown ring becomes too large. We get too little spare capacity to accommodate the extra good put. And we already know that if we start coding small flows, and you tell the difference between a small flow and a long flow in advance, not that easy, we know already that that's a waste of capacity because we already know that these flows aren't going to respond to any corrective action. Okay, so the other problem that we're challenged with is overhead timing. If we send on our overhead too soon, the overhead gets dropped when our queue overflows. If we send our overhead too fast, it actually makes the queue overflow, right? If we send the overhead too late, then we've got to remember that TCP has its own error correction mechanism, and if the TCP retransmissions get there before our code can correct, then tough luck. Then we're also out of luck. So we need to compromise there, and we'll need to find something that fits in. Okay, so what have we done in order to do this? And we've been fairly good so far at replicating scenarios, at least for the sort of lower bandwidth geostationary and medium Earth orbit ones. But with the sort of above about 100 megabits per second, we weren't entirely sure whether the results that we were seeing were as a result of lack of capacity in our system or lack of capacity or whether this was an actual effect that we were seeing. So what we decided is when they came around to us early in the year and said, do you want a bit of extra capital expenditure? We said, yes, please. So we've now built a simulator. You see those 4 racks here. On the left-hand side, this is my student Lai Chan, who's actually wired all of this up. And there's been a lot of wiring up and setting up of those machines that needed doing. So that's literally been a full-time job for a year. And basically, what you see on the left-hand side here is just over 106 physical TCP receivers, mostly Raspberry Pis, a few Intel NUCs as well. And on the right-hand side and up here, you see a bunch of 23 physical senders. These are super microservers. Then here you see 5 machines that form the satellite link itself. Satellite emulator sits right in the middle. On either side, we have an encoder, decoder. Those are these 2 machines and a PEP. And a couple of copper taps down here that help us tap into traffic. And down here, these machines do nothing else but actually capture traffic. So that's our current setup. The results I'm going to show you in a moment are still with the old setup. This photo here that I showed you a moment ago was literally one that I shot the other week. We've just wired the larger version of the simulator up, and we're about to commission that next week now. Basically, this is the topology diagram of the next one. So you can see there's a satellite link here in the middle, or link chain if you wish. Island clients and world clients. And what we're doing here is we're also having an external control network that basically let us control everything here without having to go and contaminate the actual experiment network with control traffic. So we've written a lot of software for it. There's lots of stories to tell about various of those. So you learn very, very quickly how many simultaneously communicating sockets you can have on a Linux machine. You learn that certain functions of TC and NetM don't work unless you get intermediate function block devices involved. And so we learned a lot of stuff along the way. And then basically, what are the challenges in the simulation? Well, remember our flow percentage. So what we're doing as we're simulating is we're basically shooting a lot of flows across, but they are following a real-life distribution. And that real-life distribution is heavy-tailed, so cutting a long story short, what we need to do is we need to basically measure for an appreciably long amount of time so we capture enough flows so the flow statistics actually approximate the real-life distribution. So that simply means it takes time to get meaningful results out of this, which is something we didn't really sort of foresee right from the word go, but something we had to find out experimentally, literally. So give you an idea what we do here. So we would typically run 8-10 minutes experiment on a simulated 16 Mbps geolink in order to get a reasonable convergence for the numbers. So we'll typically get around about 30 parallel flows happening in an experiment like this. This is sort of right at the point where Q oscillation will occur. And if I run a 40 megabyte iPerf transfer on the side, that'll take me somewhere between 100 and 160 seconds ballpark. There are a large number of parameters I can now set just for my baseline, the link capacity, the queue memory I deploy, so basically how large I make that input queue, the background load level or demand that I want to see, which influences this figure here. And if I then also start coding, I need to set a code generation size, overhead, retention window, number of generation groups, and a coding threshold. That coding threshold cuts out the really, really short packets, which aren't really worth coding, basically because A, they usually slip into the queue anyway, and B, they're usually part of short flows. We had to orchestrate a large number of machines in each experiment, almost 140 now. So if one of the machines doesn't do its job, we can basically throw the data for that run away. Getting clean packet capture done is always an issue, and I think that was referred to earlier on about net flow, not sampling, etc., and this sort of stuff. And so we need to do a lot of quality assurance around the whole thing, and that's just time consuming. Okay, so here's a few results. So this is an example of a baseline experiment giving throughput and good put. Throughput is the blue one, good put's the red one, for a 16 megabit per second geolink. Basically what you see here is that we're underutilizing a wee bit here. That's because we're deploying a relatively low load here. If I look at the queue sojourn time that I'm seeing here, which I can measure by putting pings through the link and measuring the RTT, what I see that I hardly ever hit the maximum here. So this is a queue that's by and large relatively empty. If I then bring this up into queue oscillation territory, what I see is that I do reach capacity quite a bit of the time, but I'm still getting times in between, and in particular also periods where I sort of go between saturation and then almost having no good put at all. So I go bang smack down here. If I increase my load, hang on, this is just the, so this is what's happening when I'm oscillating with my Q sojourn time. So you can see it sort of rises rather periodically up and down, and that's a typical symptom of that. If I'm going to a very, very high load, then basically, yes, I'm able to fill the link. However, if I'm now looking at my 40 megabyte iPerf, that basically either takes enormously long or it doesn't complete, right? So, and if I run multiple experiments, then sometimes it will complete in experiment time, sometimes it won't. So, and when I look at the Q sojourn time here at the RTTs, what you can see is that we now barely touch the baseline here. So we're getting standing queues. So this is your buffer bloat effect. If I'm running PEPs, what you see are funny things. You see those spikes going out here, right? And those spikes are simply what's happening because of the island side, PEP, and we're using symmetric PEPs, either side. If the island side PEP has a packet missing and it comes in, it then very, very quickly releases, all its buffer onto the island side connection, and that then happens at a rate that's much higher. So this is why we're seeing those shoot ups. Looking at the, so this is again at the Q oscillation, normally Q oscillation territory, and what we're seeing here is that we're in fact getting standing Qs here at times. So we're not getting quite as much oscillation, but when we're trying to measure, iPerf reports only 66 seconds transfer time. Yay, you think, but it's actually fake news. Because what iPerf tells you is how long it took to get its data across to the world side PEP. That doesn't mean the data's on the island yet, it just means we've basically posted it. So not something you, you can rely on. Okay, so if we code, what you can see here is that we're not actually doing a hell of a lot better. We're having a little less Q oscillation, so we're not really going bang smack down all the time, but we're not really doing a hell of a lot better at this point. So why is this not happening? Simple answer. We're sending, with the current version of the coding software that we have available to us, we're sending the overhead too soon and too quickly, i.e. at a much, much higher rate. Basically, the reason for this is that the normal traffic rate is basically, for the non-overhead, is determined in order of magnitude by the link rate. However, when I'm transmitting overhead, I'm transmitting this from the encoder. And the encoder, the way we've configured it, has a gigabit per second link to that satellite queue. And it's basically sending out all overhead in one go. Bang! And so what's happening at this point is that when we need that overhead most, i.e. when the queue is overflowing, what we're basically doing is we're then sending the overhead straight into the fire. And that's something that we basically need to fix, and for that we need to get that software fixed. And that's what my next sort of big goal is in terms of progressing with this project. Okay, so everybody has conclusions. I don't have conclusions yet. I'm not there yet, right? I have insights, ideas, and questions, and I'm way over time, so I'm just going to flash those up here for a moment. You can download them if you like, so to sort of see what we start racking our head about. We have a to-do list for the next little while. So next week, commissioning the upgraded version of the simulator. We've just been starting on adding UDP in, so we've written the program that we want to that, and we're currently debugging that, and that should hopefully also be ready next week. And then we want to combine PEPs and coding, and then start working on coded MEO links, because we believe that that's actually where the beef may well be. That's where we're currently seeing most of the spare capacity floating around. Then we want to delay the overhead to prevent it from getting lost in overflowing queues. Now that'll depend on a little bit of extra funding. And then there'll be lots more after that. And that's pretty much it. So thank you very much. And I'll just quickly flash up who's helped us with this, or at least the list of the people or organizations who've helped most. There are many, many more here. So thank you very much. And happy to take questions if there's time.
Okay, thank you. Any questions? Please.
Jeff Houston, APNIC. Inevitably, I have a question because I think this is fascinating. One of the early works that Van Jacobson did in doing congestion control was actually over satellite links.
Yeah.
And you've got this problem of high latency, and you're trying to add high bandwidth.
Yeah.
Congestion loss-based flow control systems always have a problem because, in essence, loss occurs after you fill the buffer, but the buffer is constructed as the delay bandwidth product. So the higher the delay bandwidth product, the greater the oscillation between peak and low, and congestion-based systems tend to suffer enormously. Come in BBR. BBR is latency-based, not loss-based. It doesn't drive the link into congestion loss. It drives at the onset of queuing, irrespective of the queue depth. Now, my experiments with BBR show that it's kind of an evolved life form because it doesn't back off with loss, it continues at full rate. And in actual fact, it maintains a fair degree of flow pressure almost irrespective of the delay bandwidth product it's driving through. My question to you is, if you flicked from doing loss-based on high bandwidth, high delay, satellite, into latency-based, using, say, BBR, would you get an entirely different outcome from your experiments?
Short answer, essentially you have 2 points where you can tackle this problem. One point is you can tackle it at the TCP sender. So you can use something else from normal that's different from normal TCP congestion control. Now the problem is when you do that, you're assuming automatically that you're having control of that sender, right? If you're having a satellite scenario like this, you're talking about the servers of the world out there, and those we have no control over. I mean, I know you would. And you're talking about clients that you're having no control over. The other point is trying to solve the problem somewhere at or around the queue. And it's tricky there because what you're getting there in terms of dynamics is that basically no queue management that you can possibly do around the queue is going to solve that problem for you.
If I ran BBR in competition to all of your congestion rate flows, would I win all the bandwidth?
Good question.
And my experiments tend to show, at least on the terrestrial network, I win.
Yeah.
I push all the others out.
Well, I mean, yes, at the end of the day you will, because, if you're not backing off, if you're not TCP friendly, you will. And in fact, that's happening to us as well when we're coding. And we're coding in one of those scenarios where we're more sort of scenario number 3, i.e. where we're having lots of short flows. We can actually take the flows that we code, and those flows will do well. But they squeeze some of those small flows, or what's left of long flows, in that link out. And we've seen that happening in Newer, for example, where we had exactly that sort of scenario on an 8 megabit per second link a couple of years ago. So yeah, that does happen. I mean, essentially, I think the philosophy behind this is to let the queue select what it wants to drop and make sure that we survive it. So the idea behind the coding, and in fact, if you look at this is actually a philosophy that's quite common in things like 3G, 4G networks, is you add forward error correction and you live with the losses. So if you don't look at a loss as a problem, but as something that will naturally occur in large numbers. And for example, if you look at the way that say information theory has been going for coding schemes, turbo codes, LDPC codes, the idea is you operate at a data rate that's larger than your channel supports, and you simply within that data rate accommodate a large amount of error correction, and then you just throw all those little bits over the fence and you see what arrives on the other end. And because of the error correction, you're able to then get a somewhat smaller good put rate out of it, but you're not having to deal with the problem of retransmissions anymore. And so that's the basic answer to this. So any scheme that you have will probably work as long as you can implement it transparently, and as long as it doesn't try to look at managing the queue. Now, part of the baselines that we did here was actually for us to find out what the optimal queue capacity would be, and it's not actually bandwidth delay product. There's a thesis from Stanford by a guy called Guido Appenzeller from a couple of years ago, who basically said take the square root of the bandwidth delay product and then divide it by the number of large parallel flows on the link. And it turns out that this one's actually a little bit closer to the truth. Now, we're finding that for us, optimum is a little bit larger than this, but it seems to be following that Stanford thesis result a lot closer than the sort of classic bandwidth times RTT formula. Right.
Okay.
Yeah.
I don't think we have time for more questions, but I think it's a very good discussion. So I would like to thank.
I'll certainly be around. Yeah.
Thank you, Mr. Ulish, again. Let's give him a big applause. And I would like to invite all the speakers to come to the stand, and let's take a picture together, please. And before the cookies run out, I think you can also enjoy the afternoon tea, and do come back in 20 minutes. I think it's we are going to start another session at 4 p.m. Okay, thank you.
Jeff's got a good article on DVR.
Yeah. I must have a closer look at that.
Yeah. Let's move a little bit.